Inside the damp, grease-slicked engine room of a steam packet docked at the port of New York in the autumn of 1851, 3 senior naval inspectors stood over a ruined locomotive crankpin. The heavy iron engine had been built in Glasgow, while the replacement pin was forged in a local Manhattan shop. By every established rule of 19th century ironworking, the 2 pieces of metal should have fitted together seamlessly. Under the flickering glare of oil lanterns, the iron journal refused to enter its housing by a tiny margin. No brass folding ruler in the entire harbor was accurate enough to detect the cause of the problem. The British chief engineer swore that the forging was too large by a 32nd of an inch. The American master machinist insisted on his professional honor that it was too small. Outside on the pier, 40 tons of fresh cargo sat waiting while 2 industrial powers argued in the dark with crude tools. At that moment, a 36-year-old clockmaker from Providence, Rhode Island, stepped quietly out of the shadows. He did not bring a wooden yardstick, squeaking iron dividers, or a clumsy workbench tool. Reaching into the pocket of his woolen vest, he pulled out a flat piece of polished tool steel no larger than a butter knife. He placed its smooth jaws against the cold iron shaft, slid a small button with a soft metallic click, and tightened a thumbscrew. Holding the instrument up to the lantern light, he read the exact dimension. This measurement was not a wild guess or an estimate handed down by old blacksmiths. It showed that the pin was oversized by exactly 0.003 inches. That tiny value equals 0.003 of an inch, which is about 1/30th the thickness of a single sheet of paper. Scottish engineers laughed at his claim, saying no hand tool could split a single hair into 10 equal parts. However, workers mounted the pin on a lathe and shaved off exactly 0.003 of an inch of metal. When they tried again, the pin dropped into its bronze housing with a tight hydraulic hiss that trapped the air inside. The ship departed on schedule, and the heated argument was instantly finished. Yet few people in that dark cabin understood that they had just seen the birth of modern mass production. Welcome to Rivet and Rebar, the channel where we explore the industrial giants and mechanical stories that built our modern world. If you enjoy forgotten history and precision machines, please take a quick moment to like this video and subscribe to support our work. Long before steel rules and steam engines transformed New England, measuring physical objects was plagued by human error. For hundreds of years, a woodworker's inch differed from a gunsmith's inch across different towns. Temperature changes added more confusion, as metal expands in summer heat and contracts during freezing winter mornings. Workshop owners used their own body parts, such as thumbs, feet, and arms, to mark off distances on raw timber and forged iron. Because no 2 craftsmen shared the same physical dimensions, parts made in one shop almost never fit machines built in another town. This total lack of standards kept industry slow, costly, and limited to small local markets. Simple tasks like assembling a water pump required constant custom fitting work. In 1631, a French mathematician named Pierre Vernier published a short paper in Brussels describing a new way to read small fractions on measuring tools. Vernier suggested placing a small sliding secondary scale next to a fixed main scale. By aligning 9 divisions on the main scale with 10 divisions on the slide, the human eye could easily spot which 2 lines lined up perfectly. Human eyesight is naturally gifted at detecting straight, continuous lines. This clever mathematical layout allowed people to read very tiny fractions with remarkable consistency across scientific studies. For 2 centuries, Vernier's clever concept remained trapped inside heavy astronomical tools, sea quadrants, and university research rooms. Instrument makers crafted these items out of expensive bronze for wealthy scientists and sea captains. Blacksmiths and factory workers could not afford such delicate devices, nor could delicate glass scales and thin bronze survive the dirty environment of a working iron foundry. As a result, Practical factory mechanics continued using crude wooden rulers and simple iron calipers for all their daily work. Skilled craftsmen relied entirely on personal experience rather than objective scientific instruments. Meanwhile, in 1833, a quiet mechanic named David Brown opened a tiny shop in Providence, Rhode Island. He repaired pocket watches, built wooden clocks, and cut brass gear wheels for local business owners. His young son, Joseph R. Brown, joined the family enterprise 4 years later in 1837. Young Joseph possessed both practical shop skills and a strong passion for extreme accuracy. He understood that careful financial management was necessary for a shop to survive, yet he spent every spare hour trying to improve measuring tools. During the 1840s, American factories grew rapidly across the northern states. Water-powered mills, gun workshops, and steam engine plants were built along fast New England rivers. Unfortunately, an expensive problem slowed down every factory floor across the nation. Every machine was built as a unique, custom prototype rather than from standardized engineering drawings. If a gear broke on a machine in Ohio, you could not simply order a standard replacement part from a factory in Pennsylvania. Instead, a local machinist had to forge a raw iron piece, turn it on a hand lathe, and slowly file it down until it fit that one specific machine frame. Workers built an industrial nation using soft iron calipers and wooden rulers marked with pocket knives. Joseph Brown recognized that American industry could never expand if every part required hours of manual hand filing. Factories desperately needed a practical measurement tool that did not rely on a worker's personal sense of touch or guess. He knew that true mass production required parts made so accurately that any part could replace another without extra fitting work. Achieving that goal required replacing rough guesswork with exact numerical standards that any worker could read quickly and accurately. He envisioned a future where every factory could produce interchangeable components with confidence. Consider how a typical machinist in 1840 measured the diameter of a spinning iron axle shaft. He picked up a spring divider, which consisted of 2 curved metal legs attached at a center pin. Dragging the sharp tips across the moving iron shaft, he judged the thickness entirely by touch. He relied on the feeling of slight friction against his calloused fingertips to decide if the size was correct. Next, he placed those divider points against a wooden ruler marked in 1/16 of an inch and estimated the remaining distance by eye. Cold weather, tired hands, or a worn wooden ruler easily caused mistakes that ruined expensive metal parts. Interchangeable parts existed only in heavily funded government armories such as Springfield and Harper's Ferry. Those military plants spent huge sums of tax money to maintain thousands of steel templates and custom master gauges. Every worker used special filing jigs to shape rifle parts to match standard models exactly. For private commercial companies, maintaining such expensive custom gauge sets was far too costly for everyday budget constraints. True interchangeability remained an impossible dream for ordinary businesses across the country. Driven by a desire for extreme precision, Joseph Brown set out to solve this big engineering problem himself in 1850. He designed and built a linear dividing engine in his Rhode Island workshop. This heavy machine could automatically etch tiny, precise graduation lines onto steel and brass rulers with incredible regularity. Before his invention, rules were marked by hand with chisels, leading to uneven spacing and frequent measuring errors. Brown's dividing engine eliminated human variation from rule making, producing the most accurate steel rulers ever made in America. Etching straight lines on steel rules was an important step, but rulers could not grip round bars or measure internal holes. In 1851, Brown took Pierre Vernier's mathematical concept and adapted it into a practical pocket tool. European toolmakers believed that a Vernier scale was too delicate for dirty factory work. Brown proved them wrong by creating a rugged pocket caliper made of hardened tool steel. He built sliding jaws mounted on a main beam marked in 20ths of an inch, adding a sliding vernier scale divided into 25 parts. Examining the mathematics behind his design reveals an elegant layout that is easy to understand. By comparing 25 divisions on the sliding scale against 24 divisions on the main beam, the tool divided each 20th of an inch into 25 equal parts. This layout allowed users to measure down to 1/1000th of an inch, or 0.001 inches. To understand how small that distance is, consider that a single human hair is about 3/1000ths of an inch thick. Brown's pocket vernier allowed an ordinary factory hand to split a human hair into 3 equal parts using a tool taken straight from his apron pocket. This new tool changed American manufacturing immediately. In 1853, Brown partnered with Lucien Sharp to form the Brown and Sharp Manufacturing Company. The two men did not just manufacture tools, they introduced trust and standard quality to American industry. Before their partnership, every machine shop guarded its own secret wooden master gauges behind locked doors. Brown and Sharp published clear tool catalogs, introduced standard wire sizes, and produced precision ground steel stock for public sale. They transformed measurement from a secret craft into an open, exact science that anyone could learn. This open approach helped build confidence among factory owners across New England and beyond. When the American Civil War broke out in 1861, the true test of precision manufacturing arrived. Union military forces required hundreds of thousands of rifles, cannons, and supply wagons built faster than ever before. Custom hand fitting was far too slow for wartime demands, and broken weapons needed fast repairs on distant battlefields. Brown and Sharp supplied thousands of vernier calipers, micrometers, and gear cutting tools to northern armories. A soldier in combat could take a lock plate from a broken rifle and fit it into another rifle without using a metal file. This high level of mechanical reliability helped support Union Army logistics throughout the Long War. Around the early 1900s, Brown and Sharp expanded into a massive factory complex on Promenade Street in Providence, spanning nearly 30 acres of brick buildings. During World War I and World War II, the company served as a central supplier for Allied defense manufacturing. Thousands of workers operated heavy machine tools around the clock in 3 daily shifts. Women joined the factory workforce in large numbers, operating milling machines, lathes, and inspection equipment. They produced famous surface grinders, milling machines, automatic lathes, and millions of precision vernier calipers. The United States military recognized their achievement by awarding the company multiple Army-Navy E awards for production excellence. Precision tools require stable metal that does not change shape after grinding. During wartime production, Brown and Sharp stored heavy cast iron machine bases in outdoor yards for many months. Exposing the raw metal castings to changing Rhode Island weather allowed internal stress inside the iron to relax naturally. This traditional seasoning process ensured that machine bases would never warp or twist after final surface grinding. As a result, tools made in Providence maintained their exact accuracy for decades under continuous heavy factory use. Now let us return to that lantern-lit steamship in New York Harbor in 1851. The real reason Joseph Brown stood on that pier holding his new caliper reveals an important story about economic independence. The steam packet carried essential components for the U.S. mail steamship line under lucrative federal contracts. British shipbuilders had intentionally built marine engines using unusual local thread sizes and custom dimensions. They hoped to force American ship owners into expensive repair contracts with overseas shipyards. This practice was an early form of commercial protectionism designed to protect British manufacturing dominance across oceanic trade routes. Through the introduction of his pocket Vernier caliper, Joseph Brown helped break that foreign monopoly for good. His small steel tool proved to federal inspectors that American mechanics could measure and build engine parts to tighter tolerances than European shops. Federal courts later used standard measurement records to resolve maritime contract disputes fairly. The pocket Vernier caliper democratized precision across the entire American nation. A young 19-year-old apprentice in Ohio, equipped with a $5 caliper, could check parts more accurately than an experienced foreman in London using old iron dividers. Standard tools allowed American factories to mass-produce steam locomotives, farm machines, sewing machines, and automobiles efficiently. Even strong industrial companies can fail when leadership priorities change over time. For over a century, Brown and Sharp was guided by experienced mechanics who spent their daily lives on the shop floor. However, during the late 1960s, corporate leadership shifted toward business managers focused primarily on short-term financial returns. To these new executives, traditional outdoor iron seasoning yards and rigorous hand inspections appeared to be unnecessary expenses. In 1964, the company moved from its historic Providence plant to a new facility in North Kingstown called Precision Park. Heavy construction debts combined with economic instability during the 1970s created serious financial pressure on the business. During the 1980s, two major challenges damaged the company's market position. First, Japanese tool manufacturers introduced high-quality digital readouts and automated machines at lower prices. Second, corporate takeover firms pressured traditional American factories to cut operating costs. Instead of investing in modern electronic research, management tried to save money by reducing worker benefits and wages. In October 1981, over 1,600 machinists walked out on strike at Precision Park. This bitter labor dispute lasted for years, causing severe hardship for local families and damaging the company's reputation. By the time legal disputes concluded, the machine tool manufacturing division was severely weakened. In 2001, a Swedish industrial group named Hexagon AB purchased the measuring tool line and brand name. The old brick factory buildings in Providence were converted into commercial shopping centers or left empty in the coastal rain. Yet while the corporate entity changed, the physical tools built by Brown and Sharp survived. In machine shops across the world, original steel Vernier calipers made decades ago remain in daily active use. They require no electric batteries or software updates, offering lasting physical accuracy. Heavy cast iron surface grinders built in the 1940s continue to grind steel to exact tolerances because their solid iron frames absorb vibrations perfectly. The company business structure dissolved, but the quality metal created by dedicated craftsmen remains a lasting tribute to American engineering. If you appreciate solid craftsmanship and historical stories about the machines that built our modern world, please share this video with fellow tool enthusiasts. Click on the recommended video on your screen to explore more fascinating stories from industrial history. Until next time, keep your machine ways clean, keep your tools oiled, and keep your measurements true.